Okay, ladies and gentlemen, let's talk about defining polynomials. Anytime I have a polynomial, that means I'm going to have some sort of function equals ax to some value, let's say 4, for example. And each of the succeeding powers is going to be a power less. So ax to the fourth plus bx cubed plus cx squared plus dx plus e. Now, of course, we're more familiar with ax squared plus bx plus c, but all this is more power, so therefore it is longer, requiring more letters. And so you simply adjust it. Now, these are called polynomials. Poly, meaning many. Nomial, nome, name, or name. So many names, okay? So in this case, we have something with many names. Really, in reality, what we have is many terms. So with many terms, we come up with this is a chunk, this is a chunk, here we go. Each of those is considered an individual piece. Now, again, little vocabulary. These are called terms. Alright, these terms are separated by operators, separated by plus or minus signs. So every one of these is a term. Now, in this case, we have a leading term. A leading term, of course, because it's leading. Now, the fact that it's first is important because in standard form they are going to be indeed first. But however, the thing that really makes it a leading term is the fact that it is the highest power. So leading term equals highest power. Now, a leading term has, of course, a couple key pieces. One of the first things we're going to have is a leading coefficient. A leading coefficient would in this case be A. In fact, it's always A because whatever it is, whatever the power is, the A is going to be listed first. And so if you have a leading term of A, you're also going to be able to do a leading term test. The leading term test tells you a couple things. First of all, it tells you, number one, the power. So in this case, we have a fourth power. The leading term will also give you the leading coefficient. It will give you the graph's orientation. So it'll give you the leading power and it'll also give you the orientation. Both of those two things are very, very important. Another thing that the leading term test will tell you is it will give you the possible number of zeros. Now, possible number of zeros is the same thing as the possible number of solutions. Possible number of x-intercepts. Zeros, solutions, and x-intercepts all mean the same thing. Also, additionally, roots. So roots, zeros, solutions, x-intercepts. All the same thing. This, by the way, is the fundamental theorem of algebra. Fundamental theorem of algebra says that there are up to the number of the highest power of solutions. So in this case, power of 4, there could be up to 4 solutions. Now, that's not necessarily saying there are, but there could be up to that many. That is indeed a fundamental theorem of algebra. Also, the leading term test gives you the possible number of turning points. Possible number of turning points, but again, it's only a possible number. It's not an exact number. We'll have to do a couple other things to determine that. But all of this is based off the leading term, which is the term with the highest power, leading coefficient, leading term test. Now, let's deal with a specific set of polynomials. So in this case, if we take something like x² minus 5x plus plus 4. If y equals that, that's fairly easy to take care of. If we factor it out, that turns out to be x minus 1, x minus 4. So our solutions are 1 and 4. So if I have 1, 2, 3, 4, I have a solution here and a solution here. You'll notice fundamental theorem of algebra says since I have a highest power of 2, I have up to 2 solutions. In this case, I've chosen one with 2 solutions. We also know that this is an even power, so that with an even power, you're going to get some sort of graph that ends up this way and ends this way. So we have something in this ballpark, 2 solutions. Now, that brings us to turning points. Now, a turning point is exactly that. It's where the graph turns around. So in this case, it comes down from left to right, turns around, and goes back up. So in this case, our turning point is right here. In our case, we're halfway between 1 and 4, so we have 2.5. 2.5, comma, something. Now, to find the something, all we'd have to do is take 2.5 and plug it in for x, and that would give us the y value of the vertex. Now, the other thing that we can do, ladies and gentlemen, is anytime you have a quadratic, if you can't factor it, you can always, of course, try to use the quadratic formula. Now, if I take another example here, y equals x squared minus 1x plus 7. In this case, if I try to do the quadratic formula, a, b, c, I have 1, negative 1, and 7. In this case, I have opposite of b plus or minus the square root of b squared minus 4 times a times c all over 2a. In this case, that gives me 1 plus or minus the square root of 1 minus 28 all over 2, which is 1 plus or minus square root of 27, which is 3 root 3, negatively speaking, all over 2. Now, the problem is if I have a negative underneath my square root, that means I have no solutions. Sort of. What it really means is I don't have any real solutions. I have 2 imaginary solutions, and we'll get to those at a little later point. But the idea is the graph here is going to look as follows. There are no solutions, no zeros, no roots, no x-intercepts. What we can say is, of course, that the vertex happens to be at opposite of b over 2a, something you learned in Algebra 2, also we've talked about, is 1/2. So my vertex is at 1/2, comma, something. Now, if I were to take care of this problem, I'd say 1/4 minus 1/2 plus 7. So in this case, I come up with 6 3/4. So I go over 1, 2, but I'm only going over a half. I'm going up 1, 2, 3, 4, 5, 6, 7. So my vertex is right here. And the other key piece is I mentioned that the leading term test says the orientation. If this first leading term, this leading coefficient, is positive, in this case positive 1, unwritten, or in this case positive 1, that means it's going to open up. So for orientation, positive means opens up, or at least opens in standard direction. Negative, of course, means opens down, or in non-standard direction. So in our case, we have a vertex here, we know it opens up, and that makes sense because we have no solutions. So by looking at the power of the leading term, the sign of the leading term, we can tell a number of key things. One is the number of possible solutions. In this case, square meant 2. Here, square meant none, no real solutions. Positive meant up. Positive meant up. And in this case, there was a 1 turning point here and 1 turning point here. Turning points. The number of turning points is always equal to power minus 1. And again, it's possible turning points equals power minus 1. And we'll talk about that here in just a second. To finish up this piece of the puzzle, we need to finish talking about the following. We need to start looking at a couple powers. The other thing that leading term test tells us is the power. Now, we've seen x squared like this, where it has two solutions. We've even seen x squared where it had no solutions. But you can also have x squared where you have a single solution. In this case, x squared itself meets only at 0, but it has x equals 0. Now, if I were to take something of the following, if I said this one, where it just comes down and touches at 1, the equation for this would be x minus 1 squared. What that means is 1 is the solution, but x minus 1 happens twice. So I have two solutions. They just happen to be exactly the same. We call these solutions of multiplicity 2. If you have an even number on the multiplicity, it's just going to touch or be tangent to the x-axis. If you have an odd number, it's going to go through. Now, we also have seen a cubic function where it crosses just once here at 0, 0. In this case, we have a cubic function, but it's going to have a number of other pieces that go along with it. And it could potentially cross 1, 2, 3 times. So remember, fundamental theorem of algebra says it can cross up to 3 times, but it may not cross all 3 times. You also notice we have power of 2, 2 possible solutions, or 1 turning point, 1 less than the power. And so in that case, we come up with 1 turning point here. But over here, we have a power of 3, and I have 1 place where it turns around, 2 places where it turns around. Do remember that in even functions, the ends have to go the same way. So you have even functions versus odd functions. Okay, so if I have squared, cubed, fourth, fifth, sixth, seventh, eighth. Okay, so in this case, even function of 4, you'll notice I have 2 solutions, but remember I could have up to 4 with 1, 2, 3 turning points. 3 turning points because it's 1 less than 4. Over here for x to the 5th, I have 1, 2, 3, 4 turning points, 1 less than 5, and 1, 2, 3 solutions, not necessarily 5. So we need to begin dealing with what is the general shape of the graph, what does the leading term tell us about it, and I'm going to put a few problems for you. Okay, there's the problem. I need you to tell me the number of solutions, number of possible solutions, number of possible turning points, actual number of turning points, the orientation, the end behavior of this graph, and be able to explain why based on information from the equation.